I think that's what we want to say for now about convergence and sort of special cases, okay? Let me, I think, conclude our discussion of Sturm-Liouville theory by talking about one more example of applying separation of variables to a particular initial boundary value problem, okay? So one more application of Sturm-Liouville theory, and in particular waves on an inhomogeneous string, okay? Waves on an inhomogeneous string, okay? So we have this string, right? And when we derived the wave equation before, we assumed that we had a sort of a constant string mass density along x, okay? But let's allow that now to be a function, okay? So we have some normalized string mass here, k of x. And so if we work through the derivation again, we get utt is equal to c squared k of x u sub x, x, right? This is now our wave equation for inhomogeneous string. Let's have t be greater than 0. X will go from 0 to 1. Let's pin the ends of the string down so that we have Dirichlet boundary conditions for t greater than 0. And let's have some initial conditions, u of x 0 equals f of x, and u sub t x 0 equals g of x. X lives in 0 to 1, okay? So call this Dirichlet BCs or fixed ends, okay? And these are ICs. Okay, so what do we do first? Say it out loud to yourself. We seek separated solutions, right? So start, seek separated solutions, right? What do those look like? U of xt equals v of x, w of t, okay? If I plug this in, I get v w prime prime, okay, is equal to c squared k of x v prime w, right? Prime out here, right? And if I divide by v and w, okay, then I can write this as w dot dot divided by w. This is equal to c squared k v prime prime divided by v, okay? All right, so for convenience later, I'm gonna actually move this c squared over here. So we'll say we're dividing also by c squared. And we'll use our similar approach to before, right? This is a function of t. This is a function of x, right? So these need to be a constant, okay? And by starting with that, we can build our boundary value problems for V and W. Okay. So so let's start with V, right? If we multiply out our equation for V, we get this, right? So I've just taken the negative, right, of the of this equation, right, and I've multiplied through by V. Okay. Well, what is this, right? This is a Sturm-Liouville problem. This is LV equals minus d dx, k of x, d dx, v, right? And remember that v of 0 equals v of 1 equals 1, right? Because of our fixed ends here, okay? Well, is L symmetric? Yes. And in order to show that, we can just apply our boundary conditions, right? At the boundaries, right, which are here, x equals 0 and x equals 1. If we apply Dirichlet boundaries, right, for v equals 0 at the boundaries and u equals 0 at the boundaries, then we get 0, right? And in the language of our Sturm-Liouville problems, our function p of x is equal to k of x, right, which is positive, and v of 0 equals v of 1 equals 0. That's our boundary conditions, right? So this implies, from Sturm-Liouville theory immediately, that we have an infinite set of eigenvalues, okay? And Vn of x n equals 1 to infinity is a complete orthonormal set, okay? Great. We can even check, right, is lambda 1 greater than 0, as we should expect it to be in this case, okay? So if we check lambda 1, right, for V1's norm squared, this is equal to lambda V1 inner product is equal to L V1 V1. This is equal to the integral from 0 to 1 of minus k V1 prime prime V1 integrated with respect to x. The initial bound, if we integrate by parts, right, and then we get, applying our Dirichlet boundary conditions, that this is k of x, integral of the magnitude of x of v1 prime squared. This is assuming that v1 is real here, right? And because we know that this has, you know, norm 1, so its integrand is it's non-zero, at least you know, on at least on some set with measure. This is non-zero everywhere, it's positive, right? So this whole thing is greater than 0, right? Because we know that k is greater than 0 everywhere, okay? So we may not be able, right, to go back here and necessarily solve this eigenvalue problem by hand, but we do know that we can find the solutions to, you know, we could find the solutions to this numerically, and that if we did, we should be able to construct, you know, a complete orthogonal set or an approximation to them, okay? Now, what about the time-dependent terms, okay? If we go back to the time-dependent equations, we have now that Wn prime prime plus lambda n c squared Wn is equal to 0. Lambda n is greater than 0, okay? And so immediately, right, this one's not hard to solve because we don't have variable coefficients or anything. It's just going to be sines and cosines, right? So we have sines and cosines, and their frequencies are given by c times the square root of lambda n, which are all positive, right? So at the end of this, we have a candidate solution, which is u of xt, the sum from n equals 1 up to infinity, an cosine of c, square root of lambda n t, plus bn sine c, square root of lambda n t, vn of x, right? Which we don't have explicit formulas for those, but we know that they exist, okay? Lambda n and vn of x, these are the eigenpairs. They're going to depend on k of x, okay? But we do know they exist, right? So that's great, okay? Well, assuming we could get these, right? Our last step is just how to obtain an and bn, okay? Well, what do we have at our disposal, right? Let's go back and look. We have our initial conditions here, okay? So we just apply our initial conditions, right? U of x0 is equal to some function f of x. As long as that's L2, we can go ahead and say, well, this is going to be equal to some n equal 1 up to infinity, an vn of x, right? I got a complete orthonormal set, no problem constructing that. In particular, an is going to be, right, is going to be equal to the inner product of f with bn. This is equal to the integral from 0 to 1 of f of x, vn of x, assuming vn of x is real. And we have a formula for all those coefficients, assuming that f is L2. U sub t of x0, remember this is g of x. Well, that's going to be equal to the sum from n equals 1 to infinity of bn c square root of lambda n vn of x, right? Because those just come down by differentiating this, right? And yeah, and plugging in time equals 0. So this implies that bn is equal to 1 over c square root of lambda n, which is fine because those are all positive, right? So this is equal to 1 over c square root of lambda n, integral from 0 to 1, g of x, vn of x dx. And this is fine as long as g is L2, okay? So we did it, right? I mean, aside from getting the vn's of x's, right, which is going to depend on the particular k of x we have, maybe we have a way of solving that in some instances, right? So what can we say now about u of xt, okay? Well, it satisfies our ICs and DCs in the L2 sense, right? Which means that it's going to L2 converge to those initial conditions we had, okay? Now, to satisfy the equation, okay, we're going to need estimates on the series solution, okay? And so we could have, for uniform convergence, okay, we would need regularity on F and G, okay? And so we can check convergence of the solution, right, using these principles of study of symmetric Sturm-Liouville problems, right? Okay. Also, right, if we wanted to really be sure, we could use something like, you know, just essentially ensuring the proper continuity of F and G, right? We would know that we have uniform convergence, right, by plugging the solution back in and putting bounds on